Welcome back, everybody. We're starting section 2.3, in which we're going to be learning about the roots of quadratic equations. And there's only one learning goal here, so that's kind of nice for us. Only one video for this section that we're going to be watching. And that learning goal is going to ask us to do this. You're going to learn to evaluate the discriminant of a quadratic function. And what you'll do with that discriminant is determine the number and type of solutions that a quadratic equation has. Alright, now a little background from Algebra 2. You might remember that a quadratic equation can have real numbers for solutions, but it can also have imaginary numbers for solutions. And this thing called the discriminant can help us decide whether the solutions would be real or imaginary. And it can also tell us how many of those solutions exist. Now I want to do a quick review with you. In our first video in this chapter, I had to explain to you what the solution of a quadratic function is. And basically we said that if you're looking at the graph of a quadratic function, that it's the x-intercepts of the graph. So right here and right there that determine the solutions of the equation. And those x-intercepts are also called roots. And really how this works is simply this. If you look at the graph of a quadratic function, such as we're looking at this one right here, if you see two x-intercepts, that means the graph has two real numbers as roots. If you saw one x-intercept, it would have one real number root. If you didn't see any x-intercepts, it would not have any real numbers for roots. With that in mind, here's what I would like you to do right now. I've given you the equations of three functions, very similar to one another, alright? Only the constant at the end changed. That's not the point though. What I'd like you to do is to graph the following functions on your calculator and then tell how many real roots it has. Does it have two real roots? Does it have one real root? Does it have no real roots? How many real roots does it have? So pause, graph each of these on your calculator, see what you determine. And let's talk about what you should have determined. Here are the graphs that you were looking at. And I just told you on the previous slide that we were trying to look at how many x-intercepts does the graph of a function have if we're going to determine how many roots it has. Now you see this first graph, there's one x-intercept, so that means there's one real solution. I'll write that down in a moment. This next graph doesn't touch the x-axis at all, so it has no real roots. And in the third graph, there's two x-intercepts, so that graph is going to have two real roots. So this is what I wanted you to write down for each of those things. Fairly simple, right? Graph is a very handy thing whenever you're trying to find the solutions of any kind of equation really, but especially quadratics and other polynomial functions. Okay, now I want to do something else with those same equations. Well, I've modified those equations slightly. Instead of making it f of x equals x squared plus 4x plus 4 and so forth, I changed the f of x to a 0. Because if you're trying to find x-intercepts, you're going to let y equal 0 anyway, so that makes sense. And what I'd like us to do now is to use a quadratic formula to show that each equation has the number of roots suggested by its graph. Meaning, I want to show that these equations have these indicated number of roots, because that's what we found out about the same equations in the previous example. Okay, now let me start off the first one with you, because even though we're using the quadratic formula, it turns out we don't have to use it entirely in order to show what it is that we're trying to show. Alright, so x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Well, b is 4, so the opposite of b is negative 4. Alright, plus or minus. And then since b is 4, b squared is 16. And then 4 times 1 times 4 is 16. So that's our 4ac. We're going to put minus 16 there. Over 2a, which is 2, because a was equal to 1 here. And I'm going to stop at this next step for right now and come back to it later on. 16 minus 16 is 0, right? So we're going to have negative 4 plus or minus the square root of 0 over 2. I would like you to get exactly that far in solving the other two equations. Don't go any further than that, just get exactly that far. Pause the video and do it, please. Check your work with mine. If you made a mistake, go back and correct it real quick. I told you that if we got this far, we'll be able to show why the graphs had the corresponding number of roots shown. Okay, why does this one have 1, this one have none, and this one have 2 real roots? And I'm actually going to start off with the one that has no real roots because it's the one that's most obviously visible at this juncture. Do you see the reason amongst this work right here that I would be able to say that that equation has no real roots? Well, I hope that you're picking out this little guy right there. This is asking us to take the square root of a negative number, isn't it? And you know from your Algebra 2 days that the square root of a negative number is not real, it's imaginary. And so because that equation would end up giving us imaginary solutions, that means it would have no real roots. And it's that same little thing, the number underneath the square root for the other two problems, that lets us know that they do have real roots. Okay? You can take the square root of 0, can't you? That's not imaginary. You can take the square root of a positive number such as 4. That's not imaginary either. So these two are both going to have real roots. Now how come one of them has 1 real root and the other one has 2 real roots? Well, that's where the difference between 0 and something positive comes into play. Since this first one just is asking you to take the square root of 0, well, the square root of 0 is 0, isn't it? And whether you add 0 with negative 4 or subtract 0 from negative 4, you're going to get negative 4 either way. So the plus or minus is kind of irrelevant at that point. And we're only going to get one answer. We're going to get negative 2 is the real root of that equation. Whereas over here, a positive number such as 4, it is going to have a square root, isn't it? And since that positive number is going to have a square root, we're going to have something to actually add and subtract from negative 4 in order to find two different solutions. All right, you'll get negative 4 plus 2 is negative 2, divided by 2 is negative 1. That would be one of the roots of that equation. Negative 4 minus 2 is negative 6. Negative 6 divided by 2 is negative 3. There, you get two real solutions. So, if you just look underneath the radical part of the quadratic formula, it tells you whether you have a real root or an imaginary root, and it also tells you whether you have 1 real root or 2 real roots if there is a real root. And that's the purpose of this next slide, is to explain that very rule to you. Now it turns out that what we were just working with is something called the discriminant. Okay? Let me write the quadratic formula down for you real quick so I can explain that slightly more. The only part of the quadratic formula that matters when all you care about is how many solutions and are they real or imaginary that a quadratic equation has is this quantity right there, b squared minus 4ac. And that quantity, b squared minus 4ac, is known as the discriminant. Okay, the discriminant is b squared minus 4ac. And so, if the discriminant is positive, if it's greater than 0, we've seen now that that means you will have 2 real roots. If the discriminant is equal to 0, that means the equation will have 2 equal real roots. Now, another way of saying that you have 2 equal real roots is this. You say it has 1 real root. In that previous example, for instance, there were actually 2 roots for the one that had 1 real root, but both the roots were negative 2. And you don't need to say the roots are negative 2 and negative 2, so there's 2 equal ones. You can just say there's 1 real root. And then finally, if the discriminant, b squared minus 4ac, is negative, if it's less than 0, we saw that the equation will have no real roots. One last notation thing, then I'm going to let you start using this discriminant. Often, whenever we're trying to state what the value of the discriminant is, we're just going to use this Greek letter delta right there to mean discriminant. Delta starts with a D, discriminant starts with a D. That's really the only similarity that they have. But when you see this delta with quadratic functions, we're going to say that that means the discriminant. Alright, well, I'd like you to do some things with discriminants now. You see these 3 equations below. For each of those equations, I'd like you to find the value of the discriminant. Whoops, let me go back. I'd like you to find the value of the discriminant and then state the nature of the roots for each equation. And when I say state the nature of the roots, I mean, are there 0, 1, or 2 roots? And are they real or are they not real? Make sense? Alright, go ahead. It's just as simple as finding b squared minus 4ac for each of them. Check your work when you're done. And there you have it. Alright, we didn't have to find the actual roots. All we had to do was be able to show that the discriminant was negative there, so this equation had no real roots. Show that the discriminant was positive for part B, so that it had 2 real roots. And show that the discriminant was equal to 0, and thus the third equation only had 1 real root. Very simple to use the discriminant, and that's what it's helpful for, is determining the number and type of the roots of a quadratic equation. Now we're going to work a couple more problems that are going to involve discriminants right now. These will be a little bit tougher, but you understand the principles needed in order to find the solutions. Let's take a look. Alright, so what I'm asking us to do here with this pair of problems is this. We're going to find the value of p such that the equation has the indicated number of real roots. And so you see a p in this equation right there. We want to find out what value of p would make this equation have no real solutions. And then you see p in the second equation. We want to find out what value of p will make that equation have 2 real solutions. Alright, now let's think about what we know about equations that have no real solutions. What we just learned is that the discriminant of such an equation has to be negative in order for it to have no real solutions. Alright, so the discriminant has to be negative. Alright, one quick editing note. I just changed that from a 12 to a 16 to make the explanation of this one a little bit more simple. So make sure that you've made that change for me. Alright, now if the discriminant has to be negative, what that means is that b squared minus 4ac has to be negative. Now the discriminant here would be equal to this. It would be p squared, because that was our linear coefficient, minus 4 times a times c, and 4ac ends up being 64. And what we're saying then is that p squared minus 64 has to be less than 0. Alright, so we're going to solve an inequality, and it's going to tell us the values. I shouldn't say value. It's going to tell us the values of p such that the equation would have the indicated number of real roots. Alright, well, let's say then that p squared is less than 64. And you might think that means then as long as p is less than 8, that we're not going to have any real solutions. That's not quite true here, and I need to explain that really quickly. And I'm going to use this number line that I drew for that explanation. Sure, if p is something like 7, then p squared would be less than 64, and so we would have, something less than 64 would give you a negative value for your discriminant, and we'd have no real solutions. But that doesn't mean that everything less than 8 would make that true. For instance, let's say p was negative 10, something way over here. Well, if p is negative 10, isn't negative 10 squared 100? And 100 minus 64 is not negative, it's positive. So we can't pick anything less than 8, but what we can do is pick anything between negative 8 and positive 8. Right? Because if you pick, say, negative 7, well, 49 minus 64 is negative. But if you pick, say, negative 9, well, 81 minus 64 is not negative. Anything between negative 8 and 8 will give us no real solutions for this equation. And so you could write your answer like this, that p has to be between negative 8 and 8, or if you prefer to use your interval notation that you've learned, you could state the same thing this way, right? P could be anything from negative 8 to positive 8. Now it can't be equal to 8 either, because 8 squared minus 64 would be equal to 0. Okay, next we're going to find the value of p that makes the second equation so that it has 2 real solutions. Alright, now I'm going to let you try this one on your own. It's not going to be quite so complicated as the previous one in terms of the final answer. Think about what has to be true about the discriminant in order for this equation to have 2 real solutions, and make an inequality involving p that will help you determine what values of p will give you 2 real solutions. Try it out. And I told you this one was a little easier than the previous one. Alright, we knew the discriminant had to be positive, so it had to be greater than 0. And if you do b squared minus 4ac, you find out that the discriminant here is 289 minus 40p. And so you set that greater than 0. Remember, when you solve that inequality and you divide both sides by a negative value, that you got to turn the inequality symbol around. So you find out that p has to be less than 289 over 40. That's about 7.25. Anything less than 7.25, and this equation has two real solutions. Anything more than 7.25 basically, and this will either have one real solution or it will have no real solutions. That's how you use the discriminant. I'll see you in class.